to the picturesque Darling West Lecture Theatre. All right. Hello, I'm David, and this is a revision seminar in semester 2, 2019, and I just do this so you know what I look like. So if you ever come to the Maths Learning Centre, you'll recognise at least one person. So that's one of the main reasons, and you probably won't see me again because I'll be writing on the document camera. So it's data analytics. I haven't done a revision seminar for data analytics for a while, but you have a new lecturer, so people are a little more confused than usual. I hope he doesn't watch this. Anyway, it's too late now. I've taken some requests, and people have asked about the bit at the end of the course about sampling distributions and standard errors and proportions and blah, blah, blah. I will do my best to try and organise this information in a way that's useful. But remember that every course that teaches statistics does this a little differently. So if I'm saying something that sounds like it's not the way your lecturer says it, just stop me and let me know, okay? The general ideas will be the same, but some of the notation might be a little different. I don't know if anyone has copies of slides or things that they could give me, but if not, I'll do my best, or notes that they've written of their own. You could email them to me if you wanted as well, but I will do my best with what we've got. So what the goal today might be more about understanding what's going on, but if you have some specific questions from tutes or something that you want me to go through, I can do that as well. So it's your revision seminar. Feel free to interrupt me. Obviously, there's a limit to how much you can interrupt me. Let me get a sentence out at a time. And especially if things like, David, should that be a minus? Or in the earlier seminar today, I had written 3 on one line and written 2 on the next line instead of 3 for no reason that I understand. So if you see that sort of thing, please point it out, and you can definitely interrupt me mid-sentence if I do that. But otherwise, any questions are okay. If you think of things I've missed and you want me to say them now while I'm in the zone of a particular thing, that's fine too, okay? If I think that you're being rude, I'll let you know, but otherwise just... You right? Okay. But really, in the end, the idea is your revision seminar, so please tell me what you want when we get up to it. So I just wanted to... It's going to take me a while to get into the flow of this, and so what I'm going to start with is how I think about the whole sampling distribution hypothesis test thing. Do they call it hypothesis test in this course? Because some courses call it a significance test, so I'm just checking. Hypothesis test? Okay, cool. So this is what... Is it the majority of the course? Have we been doing this for a while, or is it like a third?
The last couple of weeks.
Just the last couple of weeks. What have we been doing until then? Random variable stuff? I mean, so like normal distributions and that sort of thing earlier? Yeah. Oh, cool. A list of topics, even better. What statistics? Why do we need it? Probability, sampling methods, central limit theorem. Okay, so confidence intervals are part of the same story as well. So we've been doing it for about 4 weeks. Okay, so it's possibly and confidence intervals. It's all part of the same idea. Oh, I have one other thing to ask. In this course, does your lecturer allow you to write a set of notes that you can take into the exam?
Yeah.
Is it at a double-sided, one page?
One page, double-sided.
Yep. At this university, it'll never be single-sided because no one really wants to bother to check. Okay. So that's all this thing. So this is all related to the similar idea. So in my head, I don't know what your lecturer said the purpose of statistics is, but for me, the main purpose of statistics is to cope with variation. I mean, that's not the purpose, that's why it exists, okay? That's why it exists. So the point is that things vary. People vary, houses vary, companies vary, days vary, things vary, they're not always the same. Anything that you could write down is not always the same every time. And so because of that variation, we need statistics. If everything was the same every time, we wouldn't need statistics, you'd just do it once and then you'd know what the answer is. So we need to cope with variation. And the big idea is that some variation is explainable. You can go, this, but because this happened, that's why these things are different. The reason why these people are different in terms of their height is because they come from different countries, that sort of thing. Or the reason why these groups of people are different in terms of how much they participate in volunteer work is because some of them are parents and some of them aren't. That sort of thing, okay? So that's the idea, that there might be an explanation for the variation, but there's always going to be some variation that is unexplained. And that's what we call random. Okay? So the big question that we have is, why are things different? So to answer these questions, that's what it's for. Okay? Any variation we see can be separated into a bit we can explain and a bit we can't explain. And we call this random. Now sometimes we can describe our randomness, and there is random and there's random. Some things are random and it's like anything in this zone, and some things are random of anything in this zone, but it's more likely to have these ones in the middle. So that's still random, and so we can be sometimes a bit more precise about our randomness, but it's still generally unexplained. They're just different and we can't tell why, they just are. Okay, that's philosophically why we have statistics and what it's for. And so the basic idea of statistics is to answer questions like this: why are things different? But it's actually much easier to answer the question of, are things different? And hypothesis tests answer those kinds of questions. So actually statistics doesn't actually answer the question of why are things different. It just answers the question of how are things different, because we can only work with the data we have. So, but this is what we're aiming for. So I draw it like this. There may be something that you measure that is different for different individuals or different times or whatever it is, and you would like to figure out if there's some other piece of information that allows you to explain it. And so this is the idea of the same sort of question that I have. So I'm just going to give you an example. You measure student grades. And we measure the number of tutorials they go to. And then we ask, can I explain changes in students' grades by the number of tutes they attend? That's an example of the sort of thing that you would do with statistics. And you would say, and this is how I would draw it. I have a picture for these things. So I have, this is grades. No, I'm going to draw it on the other side. Just give me a second. So grades is the thing I'm interested in, and it's different for different students. And I would like to try and predict what it does based on the number of tutorials. You can tell already I'm not a particularly good judge of how many words are going to fit, or how many letters are going to fit into a space. That's the idea. That's what this question is. And the question is actually asking, is there a relationship here? Or, if I know how many tutorials they attend, does it not help me at all to predict what their grade's going to be? Now, it might not be a particularly good thing at predicting. There's different levels. It might be that I can guarantee that if they go to an extra tutorial, I can be almost certain that they're going to get an extra 10 points, percentage points. Or it may be that, well, it's going to be that on average, but there's sort of going to be really variable around that. And that's the idea. So I tend to draw, it's useful for us to know what kinds of variables they are so that we can figure out the way that it does that predicting. So this is a numerical variable, it's a number. And I draw that like this. Your lecturer probably calls it quantitative? Not sure. Both? Good. Numerical's easier for me to say. And so is this. And this picture I draw here is what I draw for a numerical variable. It's a scale on which that I write the variable. Some people call it a scale variable. Certain computer programs call it a scale variable. But another example might be, for various students, well, let's just say people, re-record, what are we going to record about these people? If they own a dog, and whether they eat meat. Are they vegetarian or not, right? And we were interested in, do vegetarians... So here's my question. Ask, can I explain how likely it is to have a dog by whether someone is vegetarian or not? Eats meat. Now, obviously, that's not the whole story, right? There are many reasons people have dogs, but I'm wondering if it's possible, whether it makes a difference at all. And that's more of this story. Dog, which comes in categories of yes and no. And meat eaters comes in categories of yes or no. And this is a thing that I'm interested in. Does eating meat make a difference to how likely it is to own a dog? This I call a categorical variable. Is that what your lecturer calls it? Or do they call it qualitative? Good. I will call it categorical. So that decision of whether it's a categorical or numerical variable will make a difference to the kinds of things you can say. Like, it's not like I'm going to calculate some percentage of dog ownership. It's not like someone is 20% a dog owner, though I guess you could possibly argue that if you wanted. Timeshare, right? But they either are or they are not. And for each individual person, they're either going to be one or the other. And so really we can only talk about, sort of how likely it is for them to be yes or no, rather than what the answer actually is. So these are important things, and they're all statistical questions, and these are questions about relationships. But there are some other questions that we might ask as well, but I'm going to draw them all in this sort of way. And some of them are going to have a relationship between a category and a number as well. They are going to have relationship between numbers and numbers, between categories and categories, and between categories and numbers. And all of these are going to be there. But it can be quite difficult to figure out how to use statistics to answer these questions. And so a lot of what we do in order to do that is to conceptualize it as something different. Okay? So what we normally do is, these people here, they have dog, yes for dog, and yes for meat. And then another person has different answers, and another person has different answers, and another person has different answers, and another person has different answers. And these are all, there's not many of them, but these are the people, and you imagine there's more of them than I've drawn. And what you can do is you can group them together and say, all right, well, what I can do is I could say, these are my meat eaters. And these are my not meat eaters. And then I could, from this group, calculate the percentage that own a dog. Well, have I got that arrow around the wrong way? Yes, okay. The percentage that have a dog. And these guys, I could do the percentage that has a dog. And I could compare those two percentages to each other. And that might be my way of deciding whether meat eating makes a difference to dog ownership. Because if those percentages were pretty close, I'd go, it doesn't seem to make a difference. But if they were really far apart, I'd go, maybe it does make a difference. And that's how I do it. I conceptualize it as usually, in this story, I conceptualize it as going, well, I can separate it into groups and I can do a statistic on those groups and compare those statistics. But really, that's just a way of trying to get my data into numbers. Because I'm not going to be able to make the decision unless I can turn it into numbers, because that's what statistics is about. So I now am asking the new question of the proportion for meat eaters, is it equal to the proportion of dog owners for no meat? So I have turned my question of, is meat eating related to dog ownership, into, are these two proportions equal? Okay. I'm hoping this is, I'm just riffing at the moment, and I'm hoping this is helpful soon. But I find it easier to think about it this way when I'm trying to decide what to do, because it most naturally matches with the question I'm trying to answer. But this is what we have to do in order to match with what your lecturer wants. Right. So your lecturer would probably write it as like P1 hat equals P2 hat question mark. Does that look familiar? Yeah, okay. So, for meat eaters and not meat eaters, something like that. I probably could put vegetarian, I suppose. Okay. But there is one more thing. You'll notice that the information we wrote down about each person here was words, right? We had categories for each person, and I could put them into 4 different combination categories. But the decision that we made was about a number that belonged to a group. So we turned information that was about each individual into information that was about a group. And that's how we're going to do this. And so it's a useful thing for me to be able to think that way, to say, this is the question I'm really asking. I'm asking about individuals and being able to predict one thing from another. But what I'm going to have to do is try and figure out how to turn that into information about groups and numbers that belong to groups. So I'm just going to write that down just a second. So, a question between, these are essentially variables, right? Becomes a question about numbers calculated on groups. And that's what all of these things are doing. And even more, the next step of statistics is that you've turned your question about relationship between variables into a question about numbers calculated on groups. And then what you do after that is you turn it into a question about a single number, that you turn all of your data into one number and you ask a question about that one number. So, a number calculated on a group is called a statistic. And a number calculated from all the data in order to answer a question is a test statistic. The reason that we calculate a test statistic is that if we can turn this question about relationship between variables into a question about a single number we calculate from all of our data, then we can ask ourselves, what are the numbers that could have happened and how likely is mine compared to them? And that's what I turn it into. So this question is now, what test statistics could have happened and how does mine compare? That is now the question. And if you're comparing something that happened to all the things that could have happened, that's exactly what probability is. Probability is a comparison between what you hope will happen or what has happened, comparing to all the things that could happen. So this is now a probability question. So that's the philosophy, and I think the most productive thing for me to do is to run through this philosophy for various different kinds of hypothesis tests that you've done. Okay? I'm hoping, how are we feeling at the moment about my plan? Okay. Now, different courses have a different list of hypothesis tests that turn up. Anytime there's a p-value or a test statistic, that's a hypothesis test. Or a critical value. Does your lecturer do critical values and p-values and you have to decide based on either? Okay, great. Yeah. Okay. All right. So one final thing, and then I'll say this all again, but with a specific example. The only way that you can ask a question about comparing to things to what could have happened is to know exactly all the things that could have happened. And that is a question about theoretically what the probabilities are. And so that is why the calculations that we do are the calculations they are, because we can, with some probability theory, borrowed from the mathematicians, figure out what all the options are. You know, technically everything has a probability. It's just we might not know what it is. Okay. These are going on the website afterwards. I'll email you. Won't be till tomorrow to say where they are. They're on, you know, the page that I have for data analytics that was linked in the email I sent you. They'll go there. So, okay. Okay. You know, all the old revision seminars are for a course called Business and Economic Statistics, which is what this course was called last year. But it's roughly the same course. Content's pretty much the same. Okay. So, let's just run through some actual hypothesis tests. So, the first hypothesis test I'm going to talk about is not the first one, and they're not in the same order as in your thing. They'll be in the order they come out of my head. So it wouldn't be the worst thing for you to start pondering which ones you want to know about. So the first one in my head, let me step back a bit. Not all questions are of this type. Some questions are just what is going on in the variation of this thing. I don't have anything to explain it, I just want to know how it varies. Just want to point that out. So some things are just about one variable and not its relation to other things, but the most useful stuff that we use statistics for is about the relationships between things. Okay. Okay. So I'm going to do the Ttest for the difference in means is what your lecturer would normally call it. They probably call it the independent samples Ttest. No? I don't know what they call it. So I'm just going to need to make a... Oh, this one's an actual PowerPoint slide. Oh, they don't even give them names? Who are these people? Honestly. All right, just... It's all right. I'll be fine. You'll be fine. I will stay in one piece, as Sebastian would say. Okay. I have names for them. It's useful for you to know names for them so that you can search for them online and find resources that talk about them. So I'm going to give them names, but your lecturer, or tutor or whoever they are, talks about difference between means. So I wish I had lecture notes to look at, because I don't have that, unless anyone has them, but they're all online, so it's just not... Okay, so, I'm just going to do it situation-wise, okay? So they're going to be pictures, I'm sorry. So the first one I'm going to do is this one. I'm interested in a number, a numerical outcome, and I'm interested in a category with two categories, and I want to see whether those categories make a difference to the number. Okay, so for example, the amount of money you spend on heating and or cooling and what's this? Yeah, this is what I was looking at just then. I've got that, but thank you. The amount of money you spend on heating and cooling and whether it is winter or summer, for example. So this is season, winter or summer, and this is the amount of money you spend on something. Or it could be with people, the amount they spend on toys and whether they are a parent, which should be related. And those sorts of things. There are a lot that are about gender, but you've got to decide what the categories of gender are. So, whether someone identifies as male or not male, and the amount of time they spend sleeping. Okay? So in medicine it's a little easier because it's like, if whether your biology has a certain chromosomes or not, and whether something happens, because that makes a difference. But gender is a social construct, and so from an economics point of view, we're actually more interested in gender than sex. So anyway, that's a whole other story. Might not get into that today. This is the story, okay? And we normally pitch this as these categories cause us to form two separate groups. One group for this category and one group for this category. So for example, is there a relationship between eye colour, which will be blue, versus everything else, and height. Which is not something you care about from an economics or marketing or whatever point of view, but it's just the first thing that bothered me. And there really isn't probably a relationship between these things. That I wouldn't expect there to be. But that's the question you could ask. And so we're thinking that for each person, we can write down their eye colour, which comes in two categories, and we can write down their height, which is a number, and we can ask this question: does height make a difference? Is it affected by eye colour? Okay, so it's blue and not blue, right? And what we imagine here is that the eye colour neatly cuts people into two groups, the people with blue eyes and the people with every other eye colour. Normally you'd put under blue your hazels and your greens as well, but my mother has hazel with brown spots, which is a bit difficult to classify. Your spotted eye colours are hard to place. They're not that uncommon. So, okay, so what we do now is we imagine that this neatly cuts the world into two, the blue eyes and the not blue. And each of them, every person in this group has a height, and we can measure the average height. Because mean is a useful way to summarise a thing of numbers. So this is the question we're really wondering about, and this is what happens to it. And we would normally say like x1 and x2, for example, with a bar to say it's a mean. I mean, the question we're really asking is about the mean for all possible people, right? This is for my sample. Give me a second. This is my sample, the people in my data. But for the people in the world, they have their own mean. All the people who could possibly exist ever that I have access to, they have their own means. And they are normally called mu1 and mu2. We're familiar with those things? Yeah. So I'm pretty sure in most statistics courses these are called parameters. I'm not sure if your lecturer calls them that. Okay, and these are statistics. Okay, cool, just making sure I've got the thing. So what we are asking ourselves now, if we're asking the question of, does eye colour make a difference to height? Then I'm asking myself the question of, are these means different? That's what my question now becomes. So the other ones I'm going to do quicker than this. I just wanted to, sorry. Okay. So we had a question of, is there a relationship between these things? And we managed to conceptualize it as, are these two numbers different? Now we don't know what mu1 and mu2 are, but we do know what x bar 1 and x bar 2 are because we collected some data. And so these are going to be the things that are going to help us decide if these are equal. Right. So now comes the maths bit. The maths bit goes, there are many ways to be different, but only one way to be the same. There's only one way for these to be equal, they're the same as each other. There are lots of ways to be different. They could be 2 apart, or 7 apart, or 15 apart, or 0.1 apart. So mathematically it's easier to work with the one way than it is with all the other ways. And so we are going to imagine a world where they are equal and think, what are all the options that could happen for these if they are equal, if the mu1 and the mu2 are equal? And that's how I'm going to figure out my probability. I'm going to pick the one way and say, if they're equal, what could I expected to happen here? And I will compare what I did get to everything that could have happened. Because if the thing I did get is really unlikely compared to everything that could have happened, then maybe I don't believe this after all. But if this being true and the thing I get is like, yeah, it's totally common, well, maybe this is true. But I never know for sure. You never know for sure. That's the problem with science. You never know for sure. You know, at some point someone may come up with some other idea or some new data which contradicts what you have, and then you have to make a new theory that encompasses all of it. So you never know for sure. But, you know, human beings are pretty good at making decisions and living their lives when they almost know nothing for sure. And so we're okay with that. Okay. So the question is now that. And now we ask if it's true that mu1 equals mu2, this is called a null hypothesis. Is that a phrase that sounds familiar? Yep. Yep. If it's true that this is equal to that, then what could have happened? Because I want to compare what did happen to what could have happened. What could have happened and how does my data compare? Now that's going to be hard, right? There's all these options for what the x1 bar and the x2 bar could have been if mu1 and mu2 actually are the same. Not least of which because we don't actually know what mu1 and mu2 are. But if we're really clever, we can figure out a new calculation based on the x1 bar and the x2 bar that we do know what all the options are if mu1 is equal to mu2. And that's our test statistic. T is something like that. I'd have to go look it up. So, what T? Probably Gossett. Like, I don't know his first name. He worked for the Guinness Beer Company. He invented the T statistic. Yep. He wasn't allowed. All his research belonged to Guinness, and so but he wanted people to know, so he published under someone else's. He published under a pseudonym, and the name he used was Student. So he published under the name Student, so that he could publish his work, even though it belonged to Guinness. Because this was invented to do quality control at the Guinness Beer Company. So, yeah. There you go. That was technically the one sample t-test, but that's where it came from. So that's why people call it the student's t-test. There you go. That's my favourite bit of stats history. There are other bits, but they're less pleasant.
Questions in the Pvalue the other day had a list of 4 answers and it had the format of the t-test or whatever it was. It had, one of them was, the answer was t-test, the other one was student t-test.
Oh, for the sake of Frel.
Which one's the actual correct?
See, I don't distinguish between them, so if your lecturer does, we're going to have to figure that out.
No, but that's also the same with standard, normal, and a normal. What's the difference between that distribution?
That I can do. Okay. Normal covers all possible normals, and one of those is the standard normal. It has mean 0 and standard deviation 1. And that's the one we call Z. And all the other ones are just other normals. Right, that I can answer. Students' t-test, I don't know what the difference between that is, because the people who taught me statistics didn't distinguish between them. They're all just t-tests. I'm sorry. I would have to look very carefully at what your lecturer actually said. So if we're ever sitting down next to a computer together, maybe in the Maths Learning Centre, we can look at the slides and we can figure it out.
It was an Pvalue question.
Is Pvalue like this online thing that you had to fill out? Yeah, and that might not even match with what your lecturer thinks.
So I think it's more textbook based.
Do we know what the book is? Okay.
It's all their stuff.
Okay. So we'd have to look in their book to see what the difference is, sadly.
It does this multiple choice into mine as well, so you know, it's like 50-50.
Yeah, I knew it was a t-test. I'm sitting there looking at a t-test or student t-test.
So I know this whole situation that I'm describing here, I know as the independent samples t-test. I will actually just redo this in a second so that it's not wrapped in the story. So this t, we're asking this calculation t, if the mu1 really is equal to mu2, then when I calculate this t in all the times I could have collected this amount of data, I can imagine all the t's that could have happened and how likely they all are. So if I imagine in the situation where mu1 is equal to mu2, all the t's that could have happened, it follows from a t distribution with probably the minimum of n1 and n2 degrees of freedom, minus 1. No, n1 plus n2 minus 2. Okay, so all t's that could have happened are described by the t distribution with n1 plus n2 minus 2 degrees of freedom, which looks like this, roughly. They all look, you know, the normal distribution looks like that too. To the naked eye, they look the same, but, you know, to the probability theory people, they're different. These are all the options for what the t could have been. And this one here is 0 in the middle. And the most likely thing to happen is for it to be near 0. And so if mu1 is equal to mu2, the most likely thing to happen is for the t to be near 0. And the least likely things to happen is for t to be far away from 0. And so if I look at the t that I actually did get, and it's really far away from 0, I go, that's really unlikely. So if when mu1 equals mu2, if when that happens, the thing I got is unlikely, then maybe I don't believe that mu1 is equal to mu2. That's the reasoning. It's a proof by contradiction, but with probability. Okay, and this is called a sampling distribution. Of the test statistic. Some people just call it a distribution of the test statistic. Some people call it a sampling distribution because what it comes about is from me imagining all of the samples I could have taken and the t's that they could have produced. And I go, well, this is my t, just here. Some people call it the calculated t. I'm not sure. That's what the old lecturer used to call it, T-calc, but that doesn't sound right for you. No, that's a different thing, but thank you for mentioning it. It's good to know. No, I will need to mention that shortly. So this is my t, and if my t is really far away to the edge, then I go, oh well, that's pretty unlikely. Maybe mu1 isn't mu2 after all. And if the t's sort of nearer to the middle, I go, totally could have happened. mu1 might be mu2. It's nothing. My data is not that unusual if mu1 is equal to mu2, so maybe mu1 is mu2. Or you go, well, my data is really weird if mu1 is equal to mu2. Maybe mu1 isn't mu2. That's the reasoning. So the further out this is, the less you believe that null hypothesis. But what we need is a rule, you know, because we don't like to be all vague like that, right? That's a bit vague. What we need is a rule for which we're definitively going to say, if it's this far out, then I'm going to say the null hypothesis is not true. And if it's closer in than that, I'm going to say null hypothesis could be true. And that's called rejecting the null hypothesis. And that is the critical value of t that you were talking about. If it's further out than the critical value of t, so if it's like this, and so most people call that t star, I think, in a calculation. I don't know. Sometimes it's called t star. Just in case you're looking at online resources, that's what I call it, but anyway. If it's further out than the critical t, I think that's unlikely, and I reject this idea. But, you know, we've got this, either this or this. Maybe the critical t is here and my t is here. So it's closer in. Well, then now, does your lecturer say retain? Or do they say do not accept? Okay. Reject what, sorry? Oh, the rejection region? That's something different. So when they say the rejection region, they mean this region here. So if it falls into the region beyond the critical t, then you reject. And if it falls outside that region, then you do not reject or possibly accept. Or do they say do not reject? Do not reject. Yeah. The safest one to say is do not reject. Okay, good. Every course, there's about 12 statistics courses across the university in like first year. Every one of them uses slightly different terminology. That makes my job really hard. And that's why it's so important if you come to the Maths Learning Centre to bring notes and textbooks and stuff with you so that the staff there can try and match up to what your lecturer is doing. Okay. So let's see if we can pull apart all of the things that happened there and try and do one. Mostly you get a machine like Excel to do all the calculations for you. And past lecturers in their exam haven't gotten you to do the calculations by hand. What they've done is given you a screenshot of Excel and asked you to interpret what it means. Yeah, but I don't know what this year's lecturer is going to do. Oh, really? Well, how have we been calculating this?
With the formulas and injecting numbers.
Fabulous. Okay, good to know. Yep.
They give us a few options, right? Like they'll give us some answers and multiple choice, but we have to calculate.
Figure out which one it is. This course is way less fun than it used to be.
Sometimes you get away just by looking at it.
Yeah, some of them you can just look at it and go, oh well, as you're dividing it by 2, it's got to be smaller than it was before. Okay. But this is the general philosophy of all of them, and some people who have walked this path before us have figured out what the best calculation to do is. Okay? So, let's actually do one of these students' T-tests. Oh, sorry, whatever they call it. I call it the independent samples T-test. Okay. I'm just going to look one up because my imagination is running low. Okay. Do people in Adelaide and Melbourne spend different amounts on movies a month? I'm just pulling this one out of an online thing, but I've changed it to be Australian instead of American. Okay, that's the question we're asking, and we're going to collect data on 50 Adelaide people and 100 Melbourne people. And then the average for the Adelaide people is, pick a number. I guess if you're one person, you go to 1, it'll be about, depending on which movie theatre you go to, 12 12 to 15. If you went to 2, it'd be, let's just say it's like 20 because it's a nice round number. You know. Well, I mean, you might have gone to 3. I don't know, just picking a number. Or 2. Like, on average, people go to 2 and they're $10 each-ish. It's the experience. And for Melbourne, it is...
They've got the crown, it's $20, you need to go to the crown once.
Yeah. Okay. So, normally in a question that you're given this, it would give you this crap, and then it would give you the question that you're trying to answer. And so the specific, I mean, in my head, the picture is location, or city, I guess. And does that make a difference to movie spend? Which is a number. And this is what I'm imagining for each individual, right? There's some people who live in Adelaide and some people who live in Melbourne. And each person has a location, a city and a movie spend, and we're interested in whether we can predict differences in movie spend from city. Random story for pretend people, but you know, pretend story, pretend people. Okay. And so what we're going to do is we're going to turn this into an independent samples t-test, which means we need to turn it into a question about numbers calculated on groups. Which means what we're going to do is we're going to go, all right, so all the Adelaide people, they have a true mean movie spend per month, and the Melbourne people have a true mean movie spend per month as well, and they're going to be given letters mu1 and mu2. In my head, I would do mu A and mu M so that I can remember which one is which, but your formula uses mu1 and mu2, and I think it's what the people marking your exam are probably going to expect. So we'll do that too.
Shouldn't the question then, instead of people in Adelaide and Melbourne spend different amounts on movies each month, shouldn't it be something like, do the people in Melbourne spend more money than the people in Adelaide?
That's a good question. Depending on how that question is asked, decides what you will do at the end when you get to the T statistic. The last thing I wanted to say that I forgot to say is that this area that's beyond your T is called the p-value, and it might be just a bit above, and sometimes it might be that and the matching bit below, depending on whether you're doing two-tailed or one-tailed. So, okay, all right, just pointing that out. And you can make your decision based on figuring out, so what you normally do is you pick a p-value, like 5%, like 0.05, and you either calculate the p-value to figure out how, and you go, well, I'll calculate my p-value and I'll compare it to the p-value that I was hoping for, and if it's smaller, that means my t's further out. Or you figure out the t that would have given you that p-value, and that's the critical t. And so they're the same thing. Okay, but we'll do both here. Let mu1 be the mean movie spend in Adelaide, and let mu2 be the mean movie spend in Melbourne, right? And then we're going to ask ourselves, is the mean movie spend in Adelaide the same as the mean movie spend in Melbourne? And the null hypothesis is that they are the same because there's only one way to be the same. And mathematically it's easier to do my calculations in that situation. Now, your lecturer probably talks about an alternative hypothesis as well then. So, since my research question was, are they different? I'm not asking if one in particular is bigger than the other. I'm just saying, are they different? And so I would be just as surprised if one was more than the other or the other way round. If Melbourne was higher than Adelaide or Adelaide was higher than Melbourne, because the way that my question is asked, I don't really care which way round it is. I just want to know if they're the same or not. I mean, a real person would want to know which one was higher. And usually you ask that question second. But for the purposes of this, that's what I'm doing. Okay. And so that's my null hypothesis. This is my alternative hypothesis. And I have very carefully told my reader what the parameters are. So in some statistics courses they say, specify a null and alternative hypothesis defining your parameters. And that's what that means. You have to tell people, every time you introduce a letter, you have to tell people what the letter stands for. So, yeah. Okay. So we've already come a long way from the picture that I was thinking about, but at least I know how I got there. Okay. So, now I need a test statistic. Which is T, which as we know was oh crap, I didn't tell you the standard deviations. Don't have that information. Standard deviations $10 and $5 and $9 respectively. Okay, sorry about that. Always forget to put the standard deviations in. And the reason I forget is that usually when I do this, I just have the list of data and the computer calculates the standard deviations for me anyway, and I don't have to worry about it. I just tell it to do a t-test and it calculates everything for me, so I don't have to know what any of that data is, because I just have the list of numbers for each person. So I have trouble doing it this way. But luckily there's a formula that has an S in it, which means I can go back and remember that I need that information. Okay. Right. Technically this calculation only works properly and gives me the correct probabilities if the standard deviations are close to each other. Yep?
Could you change the denominator to be S over square root of n?
No.
Is that a different formula altogether?
Yes. That's when you've only got one group.
Right, yeah.
But I'll do that too. Yeah. So yeah, if the two standard deviations were the same, then you'd have a chance of doing that. Yeah. The S over square root of n is when there's only one group and you're not comparing it to another group, you're comparing it to a single number. So I'll do that too. Okay. So that's my test statistic. And if the null hypothesis is true, I know that that comes from a t distribution with n1 plus n2 minus 2 degrees of freedom. So if... Does your lecturer use this symbol for distributions? T is distributed according to... like that? I don't know, but that's how I would write it.
He doesn't write anything, the lecturer.
Okay.
He just picks up a slide and points at it.
Is this on the slide?
It is for maths.
It is over in maths?
Yeah, he normally just abbreviates it to DF.
Rightio. So it's T with degrees of freedom that. Okay. So just to be sure, my actual test statistic is going to be x1 bar, which was 20, minus x2 bar, which was 15, divided by, the standard deviation was 10 and there were 50 people, and this one the standard deviation was 9 and there were 100 people. Right? Good-o. and this would be a number, which I would need a calculator to figure out. And since I didn't bring one, I will do it on the Desmos. Squared over 50 plus 9 squared. Oh, thank you. So I can already tell that's actually pretty big. Sort of the usual t's range from like +2 to -2. So if it's beyond 2, then you know you're already rejecting it, no matter which one has what. Yeah. Don't have to worry about that. But anyway, I will do it properly. So that's T with 148 degrees of freedom. Okay. So, right. So these are all the T's that could have happened. And this is how likely they all are. And mine, and that's 0, 1, 2. Mine's about here. That's the picture of what's going on here. So I can already see it's really unlikely to be this big if the null hypothesis is true. But I mean, that's just my drawing. I could have drawn it differently and it wouldn't have seemed so bad. So I have two ways of dealing with this. I can either try and get a machine to tell me exactly what the p-value is. And there are, you know, a computer can do that sort of thing. Or I can figure out how far the t would have been to get my p-value exactly 0.05 and see if mine's further than that. So I need to figure out the critical t. And I'm presuming your lecturer has a table that you look up? Good-o. Does anyone have one?
Yes, I do.
Thank you. All right, beautiful. Yep. So that degrees of freedom of 148, that there's a different t distribution for every degrees of freedom. And in my head, df actually doesn't stand for degrees of freedom, it stands for distribution finder. It is the thing we use to find the correct distribution. In my head, all the distributions live in this city, and the degrees of freedom is an address, and you go to that address and you knock on the door and you ask them for a probability, and they tell you. Okay? But in this case, it's more the other way around. You say, I want 0.05, what's the t that goes with that? Okay, but we have to make a decision here. I would have been just as surprised, if I believe that mu1 is mu2, I would have been just as surprised if my t had worked out to be a big number as if it had worked out to be a negative big number. This one goes with Adelaide being bigger, and this one goes with Melbourne being bigger. And if they really are the same, both of those are just as surprising. And so I would include both, because I'm interested in both possibilities of being different. So since I'm interested in both possibilities of being different, I will think that this bit and this bit is the p-value I want. Okay? Right. So I'm going to need to figure out a critical t statistic that goes with both sides. That's Z, okay. Okay, right. So I have 148 degrees of freedom, which is off the bottom of my table. So I'll just use the, oh no, here it is, just a second. 148, it's about 150, we'll use that one. Or does your lecturer prefer you to round down?
You can actually go in between the numbers, so the difference between, like, so the 1.288 and it's 1.8.
Well, I'm not up to that bit yet. I'm looking at the degrees of freedom. So degrees of freedom tells you which row to use, and there is no row between these, so I'm just going to have to pick one. I'll pick the lower one because it will give you bigger p-values, which means it's harder to reject. So from row 140 in the table, the critical T. Now I want I want both of these areas to be less than 0.05. Oh, we didn't specify it. Let's say we want it at the 5% level. They tell you they want the 10% level or the 1% level or the 5% level. Since they didn't tell me, since whoever wrote this, which is me, didn't tell me what it was, we'll assume it's 0.05. Okay? If you don't specify, it's 0.05. Because Fisher used 0.05 when he invented hypothesis tests. So 140. So we want both of these together to be 0.05, and my diagram only tells me the one that goes with half of that. So I want the half to be 0.025. So I will go 0.025 is there. 1.977. Thank you. Okay, so the idea is that it would be exactly on the edge of the critical region if these two areas together added up to exactly 0.05. So I'm just going to draw that. So this blue area together is exactly 0.05 together, which is why when I looked in the table, since the table only gives me 1/2, that's 0.025, so I went along to 0.025 and I went down to row 140 and it was 1.977. That's how I use the table. How are we feeling about that?
So the 0.025, was that calculated using
Sorry?
the degrees of freedom on the top, so like the 0.025 in the blue? Yeah.
Yes, this looks like a degrees of freedom in the way it's written. It's actually a probability. These are the degrees of freedom. So the degrees of freedom was...
So was it already written that there was a 50% confidence?
No, I didn't. It wasn't. Since it wasn't specified, I assumed it was 5%. So I should probably go back and fix it, but there's not room. So that's the one I did. But I mean, I could check. I mean, I suppose I could see what confidence level I could get to. My T is 2.98, which is beyond the edge of this. So the p-value's got to be less than whatever that is. So it's 1.977. Since 2.98 is greater than the critical T, I reject H0. At the 5% level. And the reason it's 5% level is because this is 0.05. If I had looked at the critical value for 0.10, I would have rejected it at the 10% level. If I had looked at the critical value for 0.01, I would have rejected it at the 1% level. And this number is so big, I probably rejected at most levels. So sometimes you would... Sometimes it rejects at one and it doesn't reject at another because you come past here. And that's okay. And in fact, if someone didn't specify what the level was, I would say it rejects at this one and it doesn't reject at this one, and I just let them decide. Yeah. So the final step of this is to actually answer the original question, And the original question was, do people in Adelaide and Melbourne spend different amounts on movies a month? Well, the evidence suggests they do spend different amounts. Because the null hypothesis was that they spend the same on average. So that people in Adelaide and Melbourne, at least the ones that are similar to those in my sample, spend different amounts on movies per month on average. Because it's not to say that there aren't people in Adelaide who have the same spending than people in Melbourne. That's totally possible. It's just that on average they're different. So if you picked a random person from Adelaide and a random person from Melbourne, you'd be fairly sure that the Melbourne one would be higher most of the time, but not always. Okay. So that's how I would do an independent samples t-test. And these are the pieces that were involved. We took our information and we pitched it as about numbers. Then we took our, and then we pitched our question as a tension between two hypotheses. And then we did our test statistic. We looked it up in the correct distribution, and then we made a conclusion. And they all have those steps. So have you got a multiple choice bit in your exam and a written bit? Oh, wow. Okay.
No, he said that there's 7 questions that are multiple choice, but they're short answers, like you actually need to do some working out to get the answer, but it's a multiple choice answer.
Rightio. What's
And
the
there's true and false as well.
What's the bet that those ones always have a none of the above? So. Okay. So, let's try a different one. What time are we up to anyway? Oh, really? Got half an hour. Okay. This is complicated stuff. When's your exam?
Next Saturday.
Okay. All right, cool. So you should know that this year, those watching from the future, it's not true this year probably, whenever you're watching, but if you're still in semester 2, 2019 when you're watching this year the first year maths exams are next Tuesday, so the Maths Learning Centre will tend to get quiet after that. So there'll be a bit more room. I mean, you can come any time and we'll make time for you, but you'll be sharing us with more people before then. Okay, so I'm going to talk about the one that you were talking about with the S on root n thing. So this one's more like, so this is going to be just the one sample t-test is what I call it. And I have a feeling, though I'm not sure, that when the thingy says t-test and students t-test, it's comparing between the one sample and the two sample. But I don't know which one is which. So I actually think, based on, I reckon it might think the students t-test is the independent sample t-test. Yep.
Yeah, because if they were doing quality testing using that, they would just be testing it based on their own numbers.
So let me do this one. So the one sample t-test, which I believe is what your textbook just calls the t-test, and they call the other one the students t-test. Because otherwise, like this is the one that was invented first, and then the one that was later should be the one with a different name. But technically this is the one that was invented by a student. But anyway, so it doesn't, that's why I don't know, sadly. Okay, the one sample t-test goes like this, where you just, I'll give an example, you know, cereal, say they contain 500 grams of cereal, we measure 35 boxes from the factory and get a mean of 490 grams with a standard deviation of 5 grams. Sorry? Oh, no, you're talking about whatever's on your phone. Right. Maybe quieter. With a standard deviation of 5 grams, is there evidence to suggest the mean weight is less than 500 grams? So I'm trying to get to what you were saying before about the two different kinds of, whether you're using both tails or one tail. Okay, so this question is not about whether something is able to predict something else. Okay, I'm not saying, well, is cereal from this machine, cereal boxes from this machine, producing different results than cereal boxes from this machine. I'm just saying this factory, is it producing ones below 500? And so the question's more like this, right, Cereal weight, and there's nothing to predict it other than just the number 500. So in essence, I'm sort of saying, is the number 500 a good prediction of how much cereal there is? That's what I'm asking. So it's not a variable, it's just a single number. That's the difference. Okay. So I need to pitch this as about the means of groups, and so it seems reasonable that I just say, well, the actual mean of all possible cereals that come out of my factory is mu, and I want to know if that mu is 500 or not. So I guess it's sort of all possible cereal boxes by this process. From this factory. Okay, so this is really interesting philosophically, actually. I like talking about this. We talk about population means and sample means in statistics a lot. The population that we're interested in doesn't even exist yet, because we're actually interested in the cereal boxes that the process produces, and they haven't been made yet. And in medicine, when you do research on babies, the babies you're interested in don't exist yet. And so I find that's really cool. The population that you're interested in often doesn't exist. Not yet, anyway. Yeah. So philosophically, I think that's cool. So let mu be the mean weight of all possible cereal boxes from this factory. We are going to say the null hypothesis is that the mean is 500. Okay? Now, the reason I'm saying equals is because when we do our calculation, we have to pick a number. There are many ways to not be equal to 500, and there's only one way to be equal, and so that's the one I pick. But the alternative is, I don't really care if they're over. I mean, to be honest, I do care. If my factory is consistently putting it over, then I'm losing money, really. But for this story, this is the reason I don't like one-sided tests, because almost always you do actually care about the other side. And so that really bothers me over that anyway. But there's no choice, we have to deal with this. The alternative is that it's less. Okay. Now, that also bothers me a little that we haven't covered all possible values of mu. We've covered 500 and less than 500, and anything that's more, we sort of just don't care. Yeah, so we're really doing this. Greater than or equal to 500 or less than 500. I don't know how your lecturer writes it. Does he does the greater than or equal to, or does he just do equals? Equals, yeah, okay. So in a technical sense, it is greater than or equal to, and we're doing like worst case scenario, it's equal. Best case scenario, it's equal. Okay, so that's where we're up to. We have a null hypothesis, we have an alternative hypothesis. I specifically chose the less than because we were interested in whether it was less than or not. And that is usually implied in the story. If you have a really good story, they give you a nice compelling reason as to why they care about only that one and not the other, but exam questions don't. But if you're really doing statistics for your own purposes, you would know. Okay, so we've got hypotheses. Let's just compare to the other one. We've got a hypothesis, and then we got, so we set up the parameter, we've got hypothesis, and then we need a test statistic. So you will find things that are based on number outcomes tend to be T's. Things that are based on category outcomes tend to be Z's. So, yep. Things that are based on number outcomes tend to be T's. Things that are based on category outcomes tend to be Z's. Just because of the way that it calculates. Did you guys do the chi-squared test? Sorry? We did? Chi-squared. And it's this symbol. We're not sure. Okay. Okay. Interesting. Okay. Okay. Feels like it wasn't covered at a deep enough level to be examinable. Okay. Okay. So test statistic is a T. And we're not, and so what we're going to do is the T is always based on how far your data is from the hypothesis. And so we're going to say that it's going to be a mean minus, well, I mean, this is how you normally write it. Like that. I put the brackets on the bottom because I struggle with fractions within fractions. Yep.
Just heads up, I think we use T when the population variance is unknown.
Yep.
Is that aligned with what you were saying previously?
Yeah, so the thing is, this is one of my problems. You never really know the real population, but yes, okay. So there is a technical detail here. In this story, this sample standard deviation came from the data that I collected. It's implied that it came from my data because it came from the 35 boxes. But if I knew from previous experience that the standard deviation previously had been 6 grams, and if I made a reasonable assumption that it was still 6 grams, then that would be a sigma instead of an S. And that would make this a Z instead of a T. That's what you're talking about? Yeah. So this is the one sample t-test which goes with the population standard deviation unknown. But if you think about it, you never really know the population standard deviation. So I don't know why we even teach that. But anyway. They do always teach it in every statistics course, but it just seems like a waste of everybody's time to me. Okay. I will just note that at the end if you forget. If I forget, let me know. I'll just put a little note about that. So this S stands for a sample standard deviation as opposed to a sigma, which stands for a population standard deviation. And I also... So if you write them down, you can tell the difference based on what the information you need. Okay, so that test statistic, which is if the H0 is true, T comes from a T distribution with degrees of freedom equal to n minus 1. So in our case, 34. Which is n minus 1. So each statistical calculation you do, the T will have a different degrees of freedom, and it's to do with all the data that's going into it, and we're taking all that into account. Okay, so my T actually calculates to be 495, was it? 490, sorry. Minus the one I think it is, divided by the standard deviation and the square root of the sample size. And I really want to make that not look like an S anymore. I've actually replaced it with an actual number. So wow! Minus 11. The 0.8 seems irrelevant if we've already gone past minus 11. So I don't even need to look that up. Minus 11 is, guys, it's really annoying. That minus 11 is always going to be off the chart. But just for the purposes of making sure we've done it properly. Here's my T down here at minus 11.8, and it's looking much bigger probability than it really is. And we'll only use one side this time. And so when I look at the critical T, it's going to be way up here. So from row 30 of the table, critical T is, so row 30, and we want, oh, I did it again. I didn't say what it was. Have I got room? Yes. Use a hypothesis test at the 1% level. Let's do that. Sorry, I always forget that bit. So it's one-sided, and so I'll go down, I went to row 30, and the 1% level is here, 2.457, because this was T, 0.010. No, never going to read that. I can barely read it with my own eyes. 2.457. Now, technically, it's actually minus 2.457 because I'm over here on the left-hand side. Okay? So since minus 11.8 is beyond the critical level, we conclude that we reject. H0. And what we do is we conclude that yes. Sorry?
Yes, we're underfilling boxes.
Yes, the mean weight is less than 500. Yep. Not by much, but, a bit. So one of the problems with hypothesis testing is it doesn't really tell you about the size of the difference. It just tells you whether the difference is there. We probably would have even found a significant difference if it was at 498. You would have said, yes, we're definitely underfilling boxes, but do we care? Because
Filling boxes legally, you have.
Yeah, I know. But there's still, you know, still quite close to half of them are still over, right? Because the mean's at 498. Anyway, maybe not. Yeah, that's when you do a confidence interval. Yep.
What was the sample size?
35.
Is that how you got the row?
Yep. So the row is the degrees of freedom. Sample size was 35, which means that the degrees of freedom was actually 34. And I always go down. Down in the literal sense of the number going down, but that's actually up the table. Yeah, because that's what I was taught, was to go to the next one below. Yeah. Because you'll see that the critical value keeps getting smaller and smaller. And so if your critical value is closer in, then it's easier to reject. So you're just being safe. I mean, to be fair, in this situation, we probably should err on the side of caution and use the one above, because we should probably reject even if there's not enough evidence. Yeah, in a quality control situation, 1% level is really a bit too stringent, but this would have been fine at any level. Yeah, if you're not going to decide it's different until the 1% level, then you really don't want it to be different. Okay, so, all right. So those are two t-tests which are distinguished by, so if you want to get to the point of being able to decide which one to do, I find in my head it's easier to decide based on this drawing. Right. So the fact that it was two categories making a difference to a number, and each individual were created two separate groups, that told me it was the independent samples t-test. I knew that what was going to happen based on that original story. And in this story, when there was only one number, and I was seeing whether there was one number measured on every individual, and I was seeing whether a single theoretical number was good at explaining that, I know already that's the one sample t-test just from that picture. But I have quite a visual memory, and that doesn't work for everybody, but it works for me. Yeah. Some people, it works to tell themselves the story, and if they use the words in a certain order, it will trigger something. And so it's a useful thing to have certain phrases that you say to yourself, that you always say to yourself, so that you can, even if you're just doing it in your imagination, you can hear and it will trigger what to do, just based on how your brain works in terms of stimulus response. If you were very good, you could turn it into a flavour if that was a thing, but I don't know if that's particularly helpful. Okay. So the other ones are the ones that you mentioned earlier with the p-hats. So we should talk about them. We've got about 12 minutes, and I can fit at least one of them in. Okay. So the p-hats are right. So just easier with a story, but I call it a one sample test for proportion is the one I'm about to do. Okay. So the one sample test for proportion tends to go with a story like this. People ask whether they prefer a new soft drink flavour over the old one. Bit of market research, right? And out of pick a number, let's say 80 people. Out of 80 people, 42 preferred the new flavour. Okay. So, using a significance level of 10%. Nah, we'll use 5%. Can't be bothered. Of 5%, decide the proportion who prefer the new flavour is more than 50%. I think I've included all the information we need. Okay. So, this can be a bit confusing because there's percentages in two places here. This percentage is the significance level, which is about the p-value and the critical value, and this percentage is about that number out of the 80. So let's imagine what's happening here. We have individuals, and each individual has been asked a question, and the question has two responses. It's either old or new. So what do you prefer? And it's either old or new. And that's what we've asked them. And we haven't got any other information about these people. All we have is the answer for this question. To be fair, if you're doing real market research, you would also have demographic features as well. But, that's not the story we have, and we don't know that information. So we've got two options, and it's a category. And the option that we're actually interested in is this one. Whether they prefer the new one or not. Okay? And we are asking ourselves, well, we're not asking what causes this to be different. We're asking, can we predict what this is? So how likely is this? So we are asking ourselves, is this 50%? Is that number a good number for the percentage that belongs in that category? That's what we're asking. Okay. My E is weird. You may be able to tell from my handwriting that I was left-handed when I started school, but I was taught to write right-handedly. They didn't force me to, I just copied what they were doing. Well, decide what you will. My sister is left-handed. Yeah. My sister is left-handed. She has a left-handed mug, which I love. No. If you hold it with your right hand, it has a little hole and it dribbles down your chin. It has a little hole just under the rim. So if you hold it but your left hand doesn't have a hole. So if you hold it in your right hand, it dribbles. So the person goes, left-handed mug, that doesn't mean anything, and then they, get coffee on themselves. I think it's quite remarkable. So maybe left-handers are evil, who knows?
Isn't that what they said? That's why they make you guys all become right-handers.
I don't know. There's a famous, one of the tribes of Israel, the Benjamites, were more likely to be left-handed. And they had an entire legion of archers that were all left-handed. It's mentioned somewhere, like in Numbers or something. My dad goes on about it, and I go, it's not that special. But anyway. Okay. So that's the question we're asking. And really, the number is jumping out at us. We want to know what this proportion really is. And so we could say, let P be the true proportion of people who prefer the new flavour, right? Okay, and so we don't know what P is, but we've got a pretty good estimate for what it is. It's 42 out of 80. Now, statisticians like proportions as opposed to percentages, so we do that as a decimal as opposed to thingy. Okay, and now null hypothesis is that it is 50%. Right? Crap, it's a proportion. 0.5. And the alternative, we're interested in whether it's more than 50%. Because I suppose, I mean, if not more than half people like it, prefer it over the old one, is it really worth switching to the new flavour? That's the story I'm going for. Okay, it's pretty close to half, 42 out of 80. So I'm hoping for a retain, like a not reject. We'll see if it works out. Okay, so, all right. So we need a test statistic. So we need to turn the information we have from our data into a number that we know the distribution of, and we are going to do a Z statistic, which is going to be, or almost always get this wrong, the P hat, which is the specific P that I've calculated today, so it's the sample proportion, minus the P from the null hypothesis, divided by I think it's this. Could be wrong. I will Google it. Yes, I was right. Okay. Okay, and this is this here is the proportion in the null hypothesis. Yeah. So technically, the P without the 0 is actually just the true P, and we don't know what that is. And so back in this formula here, technically this mu is actually the mu from the null hypothesis as well. So, yeah. Okay, and if the null hypothesis is true, Z is distributed approximately as a standard normal distribution. That's how I write the standard normal distribution. A normal distribution with mean 0 and standard deviation 1. I don't know how your lecturer writes it. So this here is called the standard normal.
Did we mention it doesn't write anything?
Yeah, I know, but is it on the screen? Someone wrote it.
It is. It's on the screen.
Yeah. Oh, okay. As opposed to every other normal, which might have mean 10 and standard deviation 4 or something, you know? Yeah, so that's why it's called a standard normal, as opposed to just a random one with a random mean and a random standard deviation. It's the standard one because it has mean 0 and standard deviation 1. And because it's the one that's on the table. Okay. It's technically only approximately. It'll only actually be approximately correct if your proportion is... if you have more than 10 people in both the yes and the no category. So, okay. So let's see, my Z is working out to be the P hat, just a second, I'm going to need to figure out what the P hat is first, it's going to be easier. P hat is 42 out of 80, which I don't, sorry? Nice. Not very far from 0.5, and so my Z is 0.525 minus 0.5 out of 0.5, 1 minus 0.5 over, and what's my n? 80. I just, have you calculated that? No? Okay.
In the process of
I get 0.447 for Z. Good! Yes, I was hoping for one that we retain. Like, this is really close in. The critical Zs are about 2. Actually, for a 5% level, the critical Z is 1.96. I just happen to know that one off the top of my head. So that's the T distribution table. The Z table's here. Do you know what? The critical ones for the Z is the infinity row in the T distribution. So this row infinity, just there, see, infinity, is the Z distribution. So, cool. Reminds me of the Lego movie. Because in my head, the T distributions all live in a tower block called T towers. So, you press the lift and you go up to level 30 or whatever. So if you go up to the infinitieth floor, that's where the standard normal distribution lives. And it just reminds me of the Lego movie because Lord Business lived on floor infinity in his building. Anyway, that's the way my brain works. Okay, so when I draw this, these are all the Zs that could be. This is 0. 1 is about here, and I've got one that's about here. My critical value is like out here. So my p-value is absolutely gigantic. So from the table, the critical Z is 1.96. And so since 0.447 is less than 1.96, we do not reject H0. And so we conclude that it's not more than 50%. So the proportion of people who prefer the new flavour is not more than 50%. This is a situation in which I could actually calculate the actual p-value this time. So the p-value for this is the area up here. That yellow bit I calculated, that's the p-value. So just a second. Or the p-value. Yeah, I can look it up here. So this thing only gives me the left-hand side. Whoa. And the left-hand side is the same as the right-hand side. So I want the right-hand side of mine. The left-hand side is the same as the right-hand side. So I should look up minus 0.447. So when I go to, it's not even, minus 0.447 is about 0.45. It's 0.3264. So it's approximately 0.3264, which is definitely more than 0.05. And so therefore I retain. So p-values and critical values work in the opposite direction. Critical value gets bigger, then that means you reject. P-value gets smaller, that means you reject. Yeah. Sorry? Say that again. Critical value is bigger, means reject. P-value is smaller, means reject. So the p-value is about how much space there is beyond where you are. So it's the opposite. There's less stuff beyond, which means that I'm further out. That's basically it. That's all I have time for. I did not even cover everything. I should just say, got about... Oh, actually, and the people are probably waiting to come in. I need to stop. No, it's 2 o'clock for the next one. That's okay. Just a second. I do want to say one more thing. There is a 2-sample version of this. So I'm going to quickly squeeze it in. You're welcome. And that's when you have... so you sort of have like Group A, Group 1 and Group 2, and they have like a yes and a no, and you're trying to see whether that, and people are in one group or the other. And then this group has a P1 hat. The idea is that in Group 1, the proportion of people that say yes, right, this is P1 hat. And in Group 2, the proportion of people that say yes is P2 hat. And then you're asking, the null hypothesis is that the proportion of people that say yes in Group 1 for all possible people is the same as the proportion of people that say yes in Group 2 for all possible people. So something like saying, do people in South Australia compared to people in Melbourne prefer the new flavour? Do one of them prefer it more than the other? Or they usually do a voter thing, do they vote for Labor or Liberal? And then your alternative is, more or less or equal or not equal to. And then you say that the test statistic is a Z, which means it's from the standard normal, and it's P1 hat minus P2 hat over something that I would have to look up. No, the SP actually goes back with the T distribution. Because that's a standard deviation. Standard deviations belong to numerical outcomes. So this one would actually be... Oh no, there will be a P as well. There's like a pooled... Oh, yes. Oh. So you have like P, just a straight P hat, 1 minus P hat over N plus 1, N1. Yes, okay, got it. I'd have to look that one up. I'm just going to write it in so that it ends up on the thing. Because if I don't write it there, then people will go, where's the actual answer, people? Okay, it's the square root of P1 minus P times 1 over N1 plus 1 over N2, where P is the combined group. You combine them all together in one big group. And so you go, I don't have room for it, just a second, combined group. Yes and no, and this is what P is. Yeah. Yep.
So it's all the yeses.
Sorry?
It's all the yeses.
Yeah. Yeah. Because the idea is that if the proportions aren't different, they're not really different groups. It's just one big group. Yeah. Okay. I just wanted to say it. They're the main ones I know of. There are a couple of others, but that's the general idea, and hopefully that's enough to make sense of all of them to have the general structure. Thanks for letting me do this.